So today's video is going to talk about sample means, and we'll be looking at sampling distributions when we take means and going through some examples of how we can calculate probability and conditions and such that go along with it. Okay, so let's look at some of the rules that kind of go along with mean and standard deviation as in regards to a sampling distribution. So the mean of the sampling distribution of X bar is the same as our population mean. So this is the same as we had for proportions, right? The mean of my sampling distribution of means is the same as my population mean, same as we did with proportions, right? Notation is going to be super duper important, and we must make sure that we're doing it. And again, this tells us that mean is an unbiased estimator here. Right, so it is an unbiased estimator of the population mean, the mean of our sampling distribution. The standard deviation of our sampling distribution is calculated through this formula here, which also is on your formula chart. Okay, so you'll notice this formula is divided by the square root of our sample size. So as we increase our sample size, our values of X bar are going to be less spread out, right? So remember, standard deviation is a measurement of variability, right? How spread out our data is. And so if I'm dividing by my sample size, right, as I divide by a larger number, then my standard deviation will get smaller or my variability will get smaller. So as I increase my sample size, my standard deviation or my variability will go down. And it does that because in the formula, I divide by the standard deviation or by the sample size. Now, a condition for using this formula, though, is that of the 10% condition. So the 10% condition states that our sample size, that's our lowercase n, must be less than or equal to 1/10 of capital N, which is our population size, okay, or 10% of our population size. So I cannot use that formula if I have like a gigantic crazy sample that's bigger than 10% of my population size. And these two statements will be true, right? That I can use this standard deviation formula as long as that 10% condition is met, okay? And that the mean of my sampling distribution will be the same as the mean of my population. These two statements are true for all forms of the population distribution, for all shapes of the population distribution. So the population distribution doesn't have to have a normal distribution for you to be able to use this information. So let's take a look at this example here. Go ahead and pause it for a second and read the example. And actually see if you can go ahead and figure it out, and then we'll go ahead and check your work. Okay, so hopefully you paused it and you've tried it, and let's see what we've got here. So the question is asking the mean of the sampling distribution of X bar. So the mean of my sampling distribution of X bar is going to be equal to my population mean, which is 25 micrograms per liter. And so when it says explain there, basically what I'm saying, I need to explain why these two things are true, which is that it is an unbiased estimator. So my mean of my sampling distribution is an unbiased estimator of, so my sample mean is an unbiased estimator of my population mean, which means then that the mean of my sampling distribution is going to be equal to the mean of my population. So the next question, the standard deviation of the sampling distribution, and I need to double check that the 10% condition is met. Okay, so if I'm going to double check my 10% condition, so 10 times 10, right? So this is how many adults? Right, times 10 equals 100. So basically what this means, if I find it this way, this means this has to be my minimum population size to be able to use my standard deviation formula, right? When I'm multiplying by 10 here, that gives me my minimum population size that then my sample size would be less than 10% of. So I definitely have a population larger than 100 adults. Okay, and so I can go ahead and use my standard deviation formula, or my standard deviation formula is population standard deviation over the square root of the sample size. So 7 over the square root of 10, which gives me 2.214. Okay, so let's look at how we can use these, how we can solve these fine probabilities involving the sample mean using our normal distributions. So if we know that our population has a normal distribution, so if we know that our population has a normal distribution with our mean of mu, right, and our standard deviation of sigma, so we know that's true for our population, then our sampling distribution of x bar, so then our sampling distribution of x bar will also have a normal distribution with a mean of mu, because remember that would be, those are equal, right? And a standard deviation of using our formula there, as long as I meet my 10% conditions. So if I look at the problem here, right, the height of young women follows a normal distribution. So there's my population follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. Show your work. So what we need to pay attention to here is that this is asking about a randomly selected one young woman, not asking about a SRS or asking about a variety of samples. Okay, it's asking about one young woman. So to do this, right, I just like a regular normal problem, I'm going to draw ideally, I'm going to label my curve. Okay, I'm going to put my 64.5 here. I would probably label this slightly better than I'm going to do, but there's my 67. I want 66.5. So, and I want to know if they're taller, right? So I'm going to go that direction, right? The probability of X being greater than 66.5 based on that particular information. Okay, and so I can go ahead and I can solve this using a z-score in table A. I can solve this using my calculator, right? If I'm using a z-score, 66.5 minus 64.5 divided by 2.5. So I'm using my population parameters here, which gives me 0.8. I can go use table A, and if I use table A, the probability that z is greater than 0.8 is going to be equal to 1 minus what I see in my table A, because remember table A only shows me to the left, right? So 1 minus 0.7881, which will give me 0.2119. I could also do this with my calculator. If y'all remember how to do this on your calculator, right? You can use your normal CDF function on your calculator, and you can choose the appropriate tail, and you can go from there. Again, you would write down all that notation to make sure that you are going to get full credit. So if I'm doing it on my calculator, right, I would normal CDF, and then my lower in this case is 66.5. My upper is some big giant number, right? And my mean in this case is 64.5. My standard deviation is 2.5. And so then that would, in your calculator, you will probably write tail right. Okay. And so that would give you an area of 0.2119. It would give you the same thing. So now let's look at the second part of this problem, part B. So find the probability that the mean height of an SRS, so a simple random sample, of 10 young women exceeds 66.5 inches. Show my work. So what I need to be doing now is thinking, okay, I've got this, I'm going to be taking lots of samples here. So now I need to shift my curve a little bit here. I know that my population distribution is normal, is approximately normal. Okay, and so I need to double check that I can use my my standard deviation formula. So I need to double check that I can use that. So I need to do my 10% rule, right? So if I did 10 young women times 10 equals 100, that means I need a minimum population of young women. And there are definitely more than 100 young women. So I would say I'm covered there on my sample being less than 10% of my population. So my 10% conditions are met. So I can go ahead and calculate a new standard deviation, which is going to be 0.79. So my 10% condition is met. You may want to identify that. And now I can go ahead and I can draw a new curve. Let's see if I can get rid of this old one. Okay, sorry, I explained everything and I were having a fight about what it was going to erase and what it was not going to erase. So now I have a new curve, right? It's still approximately normal. My mean is still the same, but now I have a new standard deviation. And remember, this is my curve here this is my sampling distribution curve. So this is going to be based off of, this is going to be the shape if I took a bunch of different samples. So this is going to be a little bit different. And this time, again, I'm looking about getting a sample of 66.5. And this time, 66.5 is going to be a lot further along down my. So 66.5 is going to be somewhere way over here. And you can already tell by looking at it that our probability is going to be a lot smaller, right? This time we're looking at the probability that the mean here is greater than 66.5. So again, drawing this all out is going to give me full credit, right? It's going to help me get direction and boundaries and all of those things. I can do it with a z-score. I can do it in my calculator, both of which should give you an answer of 0.0057. So what would be ideal right now is that you go in and you make sure you can calculate and get that actual answer. So that's my probability. So thinking about our comparison there, then that this would be really rare that we would get this SRS of 10 young women that are this tall on average, right, within the sample. So let's look at some other things we can do with this. Okay, so let's look at what we call the central limit theorem. So the central limit theorem basically states that if my sample is considered quote unquote large, then my sampling distribution shape of X bar will be approximately normal. So what is considered large is a sample size usually that is greater than or equal to 30. So keep in mind, remember, again, if my population distribution is already normally shaped, if it's already approximately normal, then my sampling distribution is going to be approximately normal shaped, right? But if my population distribution is not normal shaped, then if my sample sizes are large enough, meaning about 30 or greater, then my sampling distribution of X bar will be approximately normal. So for instance, let's look at this happening here. If you look at these four examples here, you'll see I've got n equals 2, 5, 10, and 25. And as my sample size gets larger and larger, we see the shape of this distribution changing. And the larger that sample size gets, the more the sampling distribution takes on that approximately normal shape. So again, my central limit theorem states that my sampling distribution of X bar will be approximately normal regardless of population distribution shape if my sample sizes are about 30 or greater. This doesn't have anything to do with the variability within, well, officially, right? So when you're writing and you're answering things, make sure you're sticking just to the fact that it's a normal shape. Okay, this is only the central limit theorem officially only says shape. Do we see the variability getting smaller in these examples here as we go from 10 to 25? Yes. But again, the theorem only states that the shape will be approximately normal. Okay, so let's look at one final example of what we can do with this stuff. Pause this, take a second to attempt the problem on your own, and then turn it back on and see if you were able to get it correct. Okay, so according to our problem here, we've got a technician that requires to complete the work follows a strongly right skewed distribution with a mu of 1 and a standard deviation of 1 hour. So based on what we know here, we do know that our sampling distribution mean should be the same as our population mean. Our standard deviation here, so there's an SRS of 70 air conditioning units that was taken in the city. So our standard deviation here would be, it would be 1 over the square root of 70 if our 10% conditions are met. So we need to go ahead and we need to check those real quick. So if we think about it, right, we're in a large city, so we need a minimum population of at least 700 air conditioner units. I would say in a large city that you're pretty good. You would have more than 700 air conditioners. So your 10% conditions are met, right? 70 is less than 10% of all AC units